Section 3.3, Security Properties of a MAC. MACs, like all cryptographic primitives, have their oddities and pitfalls. Before going any further, I will provide a few explanations on what security properties MACs provide and how to use them correctly. You will learn, in this order, that MACs are resistant against forgery of authentication tags. An authentication tag needs to be of a minimum length to be secure. Messages can be replayed if authenticated naively. Verifying an authentication tag is prone to bugs. Section 3.3.1, Forgery of an authentication tag. The general security goal of a MAC is to prevent authentication tag forgery on a new message. This means without the knowledge of the secret key, K, one cannot compute the authentication tag, T equals MAC of K and M, on messages M of their choice. This sounds fair, right? We can't compute a function if we're missing an argument. MACs provide much more assurance than that, however. Real-world applications often let attackers obtain authentication tags on some constrained messages. For example, this was the case on our introduction scenario, where a user could obtain almost arbitrary authentication tags by registering with an available nickname. Hence, MACs have to be secure even against these more powerful attackers. A MAC usually comes with a proof that even if an attacker can ask you to produce the authentication tags for a large number of arbitrary messages, the attacker should still not be able to forge an authentication tag on a never-seen-before message by themselves. Note: one could wonder how proving such an extreme property is useful. If the attacker can directly request authentication tags on arbitrary messages, then what is there left to protect? But this is how security proofs work in cryptography. They take the most powerful attacker and show that even then, the attacker is hopeless. In practice, the attacker is usually less powerful, and thus we have confidence that if a powerful attacker can't do something bad, a less powerful one has even less recourse. As such, you should be protected against such forgeries as long as the secret key used with the MAC stays secret. This implies that the secret key has to be random enough, more on that in Chapter 8, and large enough, usually 16 bytes. Furthermore, a MAC is vulnerable to the same type of ambiguous attack we saw in Chapter 2. If you are trying to authenticate structures, make sure to serialize them before authenticating them with a MAC. Otherwise, forgery might be trivial. Section 3.3.2, Lengths of Authentication Tag. Another possible attack against usage of MACs are collisions. Remember, finding a collision for a hash function means finding two different inputs, x and y, such that hash of x equals hash of y. We can extend this definition to MACs by defining a collision when MAC of k and x equals MAC of k and y for inputs x and y. As we learned in Chapter 2 with the birthday bound, collisions can be found with high probability if the output length of our algorithm is small. For example, with MACs, an attacker who has access to a service producing 64-bit authentication tags can find such a collision with high probability by requesting a much lower number, 2 to the 32nd, of tags. Such a collision is rarely exploitable in practice, but there exist some scenarios where collision resistance matters. For this reason, we want an authentication tag size that would limit such attacks. In general, 120-bit authentication tags are used as they provide enough resistance. Requesting 2 to the 64th authentication tags would take 250,000 years in a continuous 1 gigabyte per second link, and without changing the secret key K during all this time. From RFC 2104, HMAC, Keyed Hashing for Message Authentication, from 1997. Using a 120-bit authentication tag might appear counterintuitive because we want 256-bit outputs for hash functions. But hash functions are public algorithms that one can compute offline. which allows an attacker to optimize and paralyze an attack heavily. With a keyed function like a MAC, an attacker cannot efficiently optimize the attack offline and is forced to directly request authentication tags from you, which usually makes the attack much slower. A 120-bit authentication tag requires 2 to the 64th online queries from the attacker in order to have a 50% chance to find collisions, which is deemed large enough. Nonetheless, one might still want to increase an authentication tag to 256-bit, which is possible as well. Section 3.3.3 Replay Attacks. One thing I still haven't mentioned are replay attacks. Let's see a scenario that is vulnerable to such attacks. Imagine that Alice and Bob communicate in the open using an insecure connection. In order to protect the messages from tampering, they append each of their messages with an authentication tag. More specifically, they both use 2 different secret keys to protect different sides of the connection, as per best practice. I illustrate this in Figure 3.5. In this scenario, nothing prevents a malicious observer from replaying one of the messages to its recipient. A protocol relying on a MAC must be aware of this and build protections against this. One way is to add an incrementing counter to the input of the MAC as shown in Figure 3.6. In practice, counters are often a fixed 64-bit length. This allows one to send 2 to the 64th messages before filling up the counter and risking it to wrap around and repeat itself. Of course, if the shared secret is rotated frequently, meaning that after X messages, participants agree to use a new shared secret, then the size of the counter can be reduced and reset to 0 after a key rotation. You should convince yourself that reusing the same counter with 2 different keys is okay. Again, counters are never variable length because of ambiguous attacks. Exercise. Can you figure out how a variable length counter could possibly allow an attacker to forge an authentication tag? Section 3.3.4 Verifying authentication tags in constant time. This last gotcha is dear to me as I found this vulnerability many times in applications I audited. When verifying an authentication tag, the comparison between the received authentication tag and the one you compute must be done in constant time. This means the comparison should always take the same time, assuming the received one is of the correct size. If the time it takes to compare the 2 authentication tags is not constant time, it is probably because it returns the moment the 2 tags differ. This usually gives enough information to enable attacks that can recreate byte by byte a valid authentication tag by measuring how long it takes for the verification to finish. I explain this in the following comic strip. We call these types of attacks timing attacks. Fortunately for us, cryptographic libraries implementing MACs also provide convenient functions to verify an authentication tag in constant time. If you're wondering how this is done, Listing 3.3 shows how Golang implements an authentication tag comparison in constant time code. The trick is that no branch is ever taken. How this works exactly is left as an exercise for the reader. Section 3.4 MAC in the Real World. Now that I have introduced what MACs are and what security properties they provide, let's look at how people use them in real settings. The following sections address this. Section 3.4.1 Message Authentication. MACs are used in many places to ensure that communications between 2 machines or 2 users are not tampered with. This is necessary in both cases where communications are in clear text and where communications are encrypted. I have already explained how this happens when communications are transmitted in clear text, and in Chapter 4, I will explain how this is done when communications are encrypted. Section 3.4.2 Deriving Keys. One peculiarity of MACs is that they are often designed to produce bytes that look random, like hash functions. You can use this property to implement a single key to generate random numbers or to produce more keys. In Chapter 8 on secrets and randomness, I will introduce the HMAC-based key derivative function, or HKDF, that does exactly this by using HMAC, one of the MAC algorithms we'll talk about in this chapter. The pseudo-random function, or PRF. Imagine the set of all functions that take a variable length input and produce a random output of a fixed size. If we could pick a function at random from this set and use it as a MAC without a key, it would be swell. We would just have to agree on which function, kind of like agreeing on a key. Unfortunately, we can't have such a set as it is way too large, but we can emulate picking such a random function by designing something close enough. We call such constructions pseudo-random functions, or PRFs. HMAC and most practical MACs are such constructions. They are randomized by a key argument instead. Choosing a different key is like picking a random function. Exercise. Caution: not all MACs are PRFs. Can you see why?